At this stage, we know how to find domain and range with the graph. But what happens if we don't have a graph, right? We're very familiar with the fact that not all functions have a graph, but some functions are actually presented by an equation. And so what do we do to find the domain and range? Well, the first bit of news is the range is very hard to find without a graph. So what my outputs are at this point definitely needs a picture. But it turns out that the domain can actually be found without a graph. There's a way to analyze my inputs and figure out what I can actually put in and what I have to actually avoid. So what it comes down to figure out what inputs we can avoid is we need to look at when does math seem to break down. So if you guys look back into your math history, even if it's recent or in the past, where does math kind of make our calculator go wrong, we get errors, or something goofy kind of happens? All right, and it turns out that there's two of them. One of them is division by 0, and I believe we actually saw that in 6.1. When I have a function, let me just get another f of x here, that's x plus 2 over, let's say, x minus 4, we can immediately see that x cannot be 4, because if I try letting x equal to 4, right, we get a division by 0, which we know to be undefined. And if I'm undefined, that means there's no y value. If there's no y value, there's no output, which means this is a very bad input value. So division by 0 is a situation that we're going to try to avoid. The other one is when we try to take the square root of a negative number. We're going to talk more about this in chapter 10, but I think you guys have probably seen enough math to know that taking the square root of negative 4 in reality is a little tough, because we're trying to find a number that when I square it gives us negative 4. And one of the candidates could be 2, but when I multiply 2 to itself I get positive 4, and another candidate is negative 2, but we also get positive 4. So there's no real number that I can square to get negative 4. So this is also undefined. So we're going to try to avoid that. So how can I use this to my advantage? Well, what we're going to do is we're going to take a look at our function, and all I have to do is ask myself, are any one of these two red flags available? That's what I playfully call this. One of my red flags is division by 0. We're trying to avoid it. And one of my red flags is square roots of negative. We're trying to avoid it. So looking at this function, right, one thing we already noticed that this function is a line. And there's definitely not any square roots in it, so that red flag is handled. And then what about division by 0? Well, there is no x value down in any denominator. 3 is always defined. 3 can never be 0. And this x is being multiplied. So I don't see any red flags. And again, what I mean by my red flags is there's no division by 0 potential, and there's no square roots potential. So if there's no red flags, that means everybody's going to work. And I think we kind of get that because we all know what a line looks like, right? If we were to graph this, this would have a y-intercept at 7 and a negative slope looking like that. And so even the graph tells us that everybody's going to work. But without the graph, we would just be looking for red flags. If there's no red flags present, we have a very strong function. Next next equation is x squared minus 9x. Well, this is a degree 2 polynomial, and there is no square root, right? This is a square, not a square root. So this red flag is avoided. What about division by 0? Well, technically speaking, the denominator is equal to 1. There are no x's down in the denominator, so there is no potential for division by 0. So again, no red flags. Negative infinity to infinity is our domain. Everybody's going to work. You can throw any value in there and you're going to get something out. By the way, if we did look at a graph, we know the graph's going to be a parabola, and those usually are a U-shape. That's defined for everything. So again, the picture supports what I'm trying to say algebraically. No red flags, strong function. H of x, well, we got a problem, right? Right away, I can see that there is a potential for division by 0. I think just by inspection, right? If we add 3 to both sides, x cannot equal 3. So this basically tells me that this right there is a bad value. Anything else is going to work. So all real numbers where x is not equal to 3. So that's one way you can describe your domain. But I'm an interval notation guy. So your answer will be in interval notation. So here's 0, 1, 2, and 3. We're not including 3. That's the only value we cannot be equal to. So this means we're going to shade everything over to the left, and we're going to shade everything over to the right. So I have two intervals. This interval is negative infinity up to 3, and this interval is 3 to infinity. And then we usually connect them with a union statement. So this is how I want you guys to write your domain. So because of the division by 0, that's the situation I have to avoid. It causes an undefinition. So any other x value, anything to its left, anything to its right, is going to make this function actually work, and we'll get an output. What about this guy? Well, there is no square roots in this. Since there's no square roots, that red flag we don't have to worry about. So division by 0 came into play. It impacted what my domain is going to look like. So on to the next example. We have another rational function. So we have a potential for division by 0. So we have to worry, right? We got to make sure that that bottom is not equal to 0. So if we factor, zero factor property comes into play. And then if I do this kind of stuff, we can see that x can't be equal to negative 3 and x cannot be equal to positive 3. So these are the two input values that we have to avoid. Everybody else is going to work. These are the only two problem areas. So looking at the intervals, I would draw a number line, and on that number line there's 0. We have 3 on the number line, and we have negative 3 on the number line. We're not going to include negative 3, and we're not going to include positive 3. So we're going to shade everything to the left of negative 3. We're going to shade everything between the two values, and we're going to shade everything to its right. So this one's really complicated. I actually have 1, 2, 3 intervals where my x values are okay. This first interval is negative infinity up to negative 3. The one in between is negative 3 to 3. And the one over here is 3 to infinity. And then everything is open because we're not allowed to be equal. Union, union, you've got your domain sitting right there. So again, red flag was division by 0. We accounted for it. We threw those guys out. Here's what's left. Everything to the left of negative 3, everything between negative 3 and 3, and everything to the right of 3. Square roots, all right, we have to account for that red flag. Well, nowhere in this function is there a square root. Again, a square is different than a square root. So no red flag with regard to that. So we're done. There's my domain. Next one, again, we have another rational function. We can see that there's a potential for a division by 0. Matter of fact, let's cut this to the chase. There's no square roots. So this one's not present. This one we have to account for. So what we saw back in chapter 6 is, again, we can factor. I'm a guesser and a checker, so I believe that factors is that. Zero factor property says we don't want that to be 0, and we don't want that to be 0. Adding 2 and subtracting 1, we get x can't equal 2, and we get x can't equal negative 1. So when I look at my domain, right, let's go to our x-axis. Here's 0. There's negative 1, and we're not including it. Here's positive 2, and we're not including it. So these two areas are open, but we're now talking about everything to the left of negative 1, everything between them, and everything to the right of 2. So we, again, like this guy, we have 3 intervals. So negative infinity to negative 1 describes that interval. Negative 1 to 2 describes this interval. And 2 to infinity describes that last interval. Union, union, and we're all finished and ready to go. All right. Last but not least, again, we're going to see more of this in chapter 10. So I'll just kind of fly by this one a little bit. But the denominator is 1, so we don't have to worry about any division by zeros. But I do see a square root. So I have to make sure that whatever's inside here, it's not negative. I want to make sure that x plus 1 is positive. All right? And so we're actually going to use an inequality to say that. I want to make sure that x plus 1 is greater than, and we can actually be equal to 0. And so x plus 1 is greater than or equal to 0, subtract 1 from both sides, and we get that x is greater than or equal to negative 1. If I try to graph that on a number line, there's 0, here's negative 1. We're allowed to be equal to negative 1, and then we're greater than negative 1. So we're shading everything to its right. So interval notation would be negative 1, 2, that's a negative 1 there. Close bracket for negative 1 because we're including it, open for infinity. So that is how we look for a domain without a graph. You're basically trying to figure out where's my red flags. If there are no red flags, you're a strong function, everybody's going to work. If you have a division by 0, you have to account for it, throw them out, and then consider everything that's left behind. If you have a square root, you have to remain positive, which usually means we're going to set up an inequality like so, and then solve the inequality and get that. More on this in Chapter 10. I'm pretty sure you'll see a lot of this in your homework in 7.2. All right, one more video to cut, and we're done with 7.2. See you then.